This video will see about the entropy. So in the thermodynamics there are coordinates such as pressure, volume, temperature and internal energy. These are the most important point functions used to describe a thermodynamic state of any system. In 1854, Clausius introduced one more coordinate, and that variable of a new coordinate is entropy. We are knowing most of the examples of a thermodynamic process, that water will flow by itself only from higher level to a lower level. And one more example is that the electricity tends to flow only from a point of higher potential towards a point of lower potential. So what is meant by the entropy? We will see in this video. And there are many reversible and irreversible processes takes place. Okay, so we see what is meant by the entropy. So first of all, in the 1854, Clausius introduced this term, the entropy. So here consider a system consisting of n Carnot cycle performing a cyclic process. So I will draw a Carnot cyclic process. So here consider a system of n reservoirs performing a cyclic process consisting of a sequence of states. They interact with a series of heat reservoirs, say R1, R2, R3 and Rn. Reservoirs whose temperatures, so first of all we will write the reservoir's name, it is n number of reservoirs at a temperature T1, T2, T3 up to the Tn respectively. Let H1, H2, H3 up to Hn be the heat transfer. Transferred with them. Then Clausius theorem is the relation between the temperature of the reservoir and the heat exchange, and it states that summation of I is going from 1 to n Hi upon Ti, or we can write summation of I is going from 1 to n delta Hi upon Ti is less than 0. And it is true for any cyclic process may be reversible or irreversible. Then system absorbs the heat are positive and negative when system rejects the heat. Okay. To derive Clausius theorem, consider this figure. Let here R0 be the heat reservoir that works as a heat engine at some arbitrary temperature T0, and N Carnot's engine say C1, C2, C3 up to Cn are work as a refrigerators operating between the temperature T0, T1, T0, T2 up to this T0, Tn respectively as shown in this figure. It is necessary to adjust the size of a cycle in a system so that the quantity of heat rejected by the Carnot cycle C1 is T0 T1 for a C2 heat rejects from T0 to T2 up to the Cn who rejects the heat T0 to Tn at the temperatures during any cyclic transformation. So in this cyclic process, the quantity of work performed is equal to the heat absorbed during the process. There is no restriction here on the direction of interchanges of the energy, maybe either from R0 to Rn or Rn to R0. So only one restriction, and it is that the changes should be consistent with the first and the second law of thermodynamics. Here, what is the restriction here? That the changes should be consistent with the first and the second law of thermodynamics. In this above composite cycle, now consider a complex cycle. Here we will consider a complex cycle that consisting of the cycle performed by these S systems, and each of Carnot cycle considered only one. Here each of Carnot cycle considered only one. We have complex cycle, we can write complex cycle is equal to S cycle plus C1 plus C2 plus Cn, so that the system S becomes back to this initial state, and also no reservoirs R1, R2 and Rn gains or loss heat during this complex cycle. So the net quantity of heat we can write, therefore the net quantity of heat drawn from the reservoir R0 at temperature T0 is, we can write summation of I is going from 1 to n, Hi0 is equal to H0 we can write as a T0 summation of I is going from 1 to n Hi upon Ti. So for a typical cycle we can write for a typical cycle we can write Hi0 upon Hi is equal to T0 upon Ti. Okay, but in this any cyclic process, the heat absorbed during the process is equal to the net amount of work performed. Means heat absorbed by the cycle or during the process is equal to the net amount of work performed by that process during the process. So in our complex cycle mentioned in above, the system S gets back to its initial thermodynamic state on completion of cyclic process. Reservoirs R1, R2, Rn do not gain or lose heat. Do not gain or lose any heat. The quantity of heat absorbed from this reservoir R0 at the temperature T0 is equal to, we can write, that is T0 summation of Hi upon Ti. This should be transformed into equivalent work. Okay, it means H0 extracted from the reservoir R0 at T0 must be converted into equivalent work. But this violates the Kelvin's Planck statement of thermodynamics second law. What that law states, it is impossible to get a continuous supply of work from a body that can transfer heat with a single heat reservoir. So according to the second law of thermodynamics, gives the condition under which heat can be converted into work. So we can write W0 is equal to H0, or H0 means what? We can write T0 summation of Hi upon Ti. Now according to the second law, this quantity should be less than or equal to 0. So we can write therefore T0 summation of I is going from 1 to n Hi upon Ti is less than 0. So dividing by this T0, so we can write dividing by T0, we can write summation I is going from 1 to n Hi upon Ti is less than 0. For a system, if that system consists of a large number of reservoirs, if there are n number of reservoirs, we can write the above equations as, that is H1 upon T1 plus H2 upon T2 plus Hn upon Tn, that should be less than 0. This is the Clausius theorem. What? This is the Clausius theorem. If the number of reservoirs are infinite and the heat exchange occurs by an infinitesimally small amounts, that is a delta H. So we can write above equation as a delta H upon T is less than 0, where the symbol, it means that this is a sum over the entire cycle, and delta H is an infinitesimally quantity of heat absorbed by the system. By that system.